Work has to be done on an object to increase its kinetic energy. If an object is already moving, work is required to stop it. The change in kinetic energy is equal to the net work done. The work-energy theorem describes the relationship between work and energy. We abbreviate change in with the delta symbol. Work equals a change in kinetic energy. The work in this equation is the net work, the work based on the net force. If there's no change in an object's kinetic energy, then no net work was done on it. Push against a box on a floor. If it doesn't slide, then you aren't doing work on the box. If there's no friction at all, the work you do on the box is the force of your push times the distance. This work becomes the kinetic energy of the box. If there's some friction, it's the net force of your push minus the frictional force that's multiplied by the distance to give the gain in kinetic energy. If the box moves at a constant speed, you're pushing on it just hard enough to balance friction. The net force and net work are zero, and according to the work-energy theorem, the change in kinetic energy is also zero. The work-energy theorem applies to decreasing speed too. The more kinetic energy something has, the more work is required to stop it. Twice as much kinetic energy means twice as much work. When a car brakes, the work is the friction force supplied by the brakes multiplied by the distance over which the friction force acts. A car moving at twice the speed of another has 4 times as much kinetic energy and will require 4 times as much work to stop. The frictional force is nearly the same for both cars, so the faster one takes 4 times as much distance to stop. More important than knowing what energy is understanding how it transforms. We can understand nearly every process that occurs in nature if we analyze it in terms of a transformation of energy from one form to another. Potential energy will become the kinetic energy of the arrow. As you draw back the arrow in a bow, you do work stretching the bow. The bow then has potential energy. When released, the arrow has kinetic energy equal to this potential energy. It delivers this energy to its target. The small distance the arrow moves multiplied by the average force of impact doesn't quite match the kinetic energy of the target. However, the arrow and target are a bit warmer by the energy difference. Energy changes from one form to another without net loss or a net gain. The study of the transformations of energy from one form into another is called the law of conservation of energy. For any system in its entirety, as simple as a swinging pendulum or as complex as an exploding galaxy, there's one quantity that does not change: energy. Energy might change form, but the total energy stays the same. Part of the PE of the wound spring changes into KE. The remaining PE goes into heating the machinery and the surroundings due to friction. No energy is lost. Everywhere along the path of the pendulum bob, the sum of potential energy and kinetic energy is the same. Because of the work done against friction, this energy will eventually be transformed into heat. When the woman leaps from the burning building, the sum of her potential energy and kinetic energy remains constant at each successive position all the way down to the ground. Each atom that makes up matter is a concentrated bundle of energy. When the nuclei of atoms rearrange themselves, enormous amounts of energy can be released. The sun shines because some of its nuclear energy is transformed into radiant energy. In nuclear reactors, nuclear energy is transformed into heat. Enormous compression due to gravity in the deep hot interior of the sun causes hydrogen nuclei to fuse and become helium nuclei. This high temperature welding of atomic nuclei is called thermonuclear fusion. This process releases radiant energy, some of which reaches Earth. Part of this energy falls on plants, and some of the plants later become coal. Another part supports life in the food chain that begins with microscopic marine animals and plants and later gets stored in oil. Part of the sun's energy is used to evaporate water from the ocean. Some water returns to Earth as rain that's trapped behind a dam. The water behind a dam has potential energy that's used to power a generating plant below the dam. The generating plant transforms the energy of falling water into electrical energy. Electrical energy travels through wires to homes where it's used for lighting, heating, cooking, and operating electric toothbrushes.